Okay, so this is the first video example set from chapter 14 where we're looking at heat as energy transfer, excuse me, rather than like the motion of particles and kinematic or kinetic theory, excuse me. Okay, so the first one we're going to look at is when we have a pot of tea and the tea is being poured into a cup. And for the purposes of this problem, we're pretty much going to assume that tea is mostly water. So when we think about things like its specific heat, we're just going to use the specific heat of water for that, okay? So the temperature of the tea at the beginning is 95 degrees. The temperature of the cup is 25 degrees. They give us the cup's mass. We better convert that to kilograms like so. So it's that many kilograms, 0.15. And they give us the volume of the tea is 200 cubic centimeters. That can't be very many cubic meters, so we'll just convert that real quick. So let's convert that to cubic meters. So we'll say, well, if we want meters on top, we better put centimeters on the bottom, so they'll cancel out. They're cubic, so we better cube everything. So whereas one meter is 100 centimeters, but if we're cubing it, we got to cube everything, and one cubed is just one. So that's really like 200 divided by a million. So it's 200 times 10 to the negative 6th cubic meters. Okay? The question is, once we pour the tea into the cup, what's the common temperature of the system after things have kind of reached equilibrium or balanced out? Okay, so T of the system is what we're interested in. What is it? So in this little section, you've learned that like the heat lost by the T, if we're just thinking about like our little system, that's got to be equal to the heat gained by the cup. So we just do those two things. And back when it talked about specific heat in 14.3, it said that if you're thinking about like heat lost, gained, you just do the mass of what you're dealing with times its specific heat times the change in temperature. So we're just going to set those two equal to each other, except on this side we have T, and on this side we have our cup. All right? So on this side, the change in temperature, we're going to go 95 minus T because we're really thinking it's a loss. And on this side, since it's a gain, we're going to say it's like T minus 25, and T is like um, then T will give us the amount gained. You really could have done that as 25 minus T over here too, except you'd get like a negative answer, which really wouldn't make sense. We're just looking for a positive answer. So don't get too worried there, but that's the way it's like opposite there. Okay, so we just plug in what we have. The mass of the T we said was what? Oh, we need to calculate that. We don't have that yet, right? Do we just have volume? So if you remember, if you have volume and need mass, that should be definitely doable from the last chapter 10, because mass is density times volume. So we said we're going to consider T as basically water, so that's really just 1 times 10 to the third for water. That's the density of water times the volume, which we said was 200 times 10 to the negative 6th. Well, I'm getting out of control here, so we take that, and if you use your calculator and get that guy down, it's about 0.20 kilograms. So that kind of makes sense that the T actually weighs a little bit more than the cup. So, okay. So then we just plug in what we need. So we go 0.20 for the mass of the T. We look up the specific heat of T, which we're going to say is just water. So flip in your book, find this guy. We say, okay, water is, oh, liquid water is right here. So you could use either of these two things. Just notice the unit difference. This one's like kilocalories per kilogram times degrees Celsius. This one is like joules per kilogram times degrees Celsius. I think we'll be using this one the most. But, I mean, just refer to the examples in the book to kind of keep track, or you can put your units in. I'm not going to do it that way, so it's kind of up to you. All right, so I'm going to use this one for this problem. That's going to work for us, all right, because we're in kilograms, we're not in grams. Okay, so what did we say that number was? 4186. All right, so 4186. Oops, it's getting a little messy. 4186, and then we've got 95 minus T equals, the mass of the cup was 5.15 kilograms. And the cup, we're going to say, let's just say it's made of glass. So we go on here and grab the value for glass. What's the specific heat of glass? It's 840 right there. So we'll put 840 in for the cup if we've got a glass cup. And then we've got T minus 25. Now we just solve for T. Now you guys should be able to do your algebra. I'll give you another step though or so from the book. So if you multiply 0.2 times that, you're going to get what? Oh, if you do significant figures, about 79,500. And then if you multiply that times negative T, you get negative 837 about T. And if you come over here, you're going to get about 126 T. That times negative 25 gives you about negative 3,150, and you keep solving down for T. I know we can do that, so add that side. I hope we can do that. It's equations of my algebra kids are doing right now. Bless their little souls, and you get 86 degrees Celsius. So let's remember what that was. That was the temperature of the system. So you want to interpret that carefully. So I said, therefore the T drops by, so that's 86. If you go back up to your original part, 86, how much does it drop by? (95 minus 86). What is that, 9 degrees? So the T only drops by 9 degrees in this heat, in this transfer. The cup gains a lot though, right? So if they're both at 86 degrees, how would you figure out how much the cup gained? Well, you could go 86 minus 25, and you'd get 61. So the cup gains a lot more. So my question is, why is that? Why does that happen? And I think the obvious answer basically is that, remember, water is this wonderful magical substance that has a lot of crazy properties. Its specific density is very valuable, but in fact its specific heat is probably more useful in industrial applications. For instance, it basically absorbs, water absorbs a lot of heat before it boils or does all kinds of things. So the specific heat of water is just that much different. So water's got special properties like that. All right, let's look at another example before I fall asleep here. Been a long day. Let's see. So let's look at 14.5. So in 14.5, we're going to talk about this instrument or device called a caloriometer. So a caloriometer is just a device where you've got basically like a bucket of water. So if you want to imagine like a bucket of water, and it's surrounded by some kind of insulating material, and you stick a thermometer in it, and basically the idea here is to figure out the specific heat of a substance. So what you're going to do is put your substance in there, and the heat lost by that substance will be gained by the water, and then you basically just measure that change. So it's kind of like this last problem. So let's look at example 14.5. So this is where a caloriometer is used. So it says an engineer wishes to determine the specific heat of a new metal alloy. He has a certain amount of it. It's heated to, so he has 0.15 kilograms. He said it's heated to 540 degrees Celsius. It's then placed in 400 grams of water, and that is at 10 degrees Celsius, so nothing extreme. And he said it's contained in a 200-gram aluminum calorimeter cup, so that's kind of what you place down in here, and you lower it into the water. So you lower this cup down in there, And so it's an aluminum cup. So we better just remember that that's aluminum. Okay. So originally when you put that cup in there, if there wasn't the heated alloy inside of it, it'd be at the same temperature too. So I said that's at the same temperature as the water because it's just going to balance out as well. And it says, okay, so after this happens, the engineer measures, and the total temperature of the system for all the different things involved after it kind of settles down to its equilibrium is 30.5 degrees Celsius. So that's what happens, that's what he measures. So now what he wants to figure out is what's the specific heat of this alloy that he has, whatever it's made of, because it might be made of a combination that's never been tested before, okay? So basically the heat lost by the alloy is equal to the heat gained by the water plus the heat gained by the cup. That's the same thing we did last time. So basically we're just going to fill that in with the same kind of relationship we had last time. So the heat lost by the alloy, we're going to say is like M A, specific heat. Jeez. So MC delta T. And the heat gained by the water will be another M, so mass of the water, specific heat of the water, times the temperature change it undergoes, plus, you guessed it, mass of the aluminum cup, times its specific heat, so that'll be for aluminum, times the temperature change it undergoes. So then we just plug those in. So the mass of the alloy was 0.15. We don't know its C, so we'll leave that alone. The temperature change it undergoes is, I guess we'll put it in there, 540. It's going to get long, minus the final, which was 30.5. Then the mass of the water was 400 grams, so 0.4. And we just said a second ago the specific heat of water was 4186, I think. And the water undergoes a temperature change of 30.5 minus, it started out at 10. Notice these have been arranged so the temperature change is positive, and so have these, because we just don't want to have to, that's just the change in temperature. It's kind of like an absolute value, so it should always kind of be positive in these problems. Does that kind of make sense? So it should be a positive value. You're just looking for the difference. Okay, and then for the aluminum, we said that was 0.2 kilograms. Aluminum, we better go look up what's aluminum. Have it, 900. So 900 for its specific heat, and it's got that same thing from the previous one, 30.5 minus 10. That's the temperature change it underwent as well. So then you just basically solve for C. So what you're going to get here when you work these numbers out is 76.4 times that C guy right there, which we were trying to figure out. We want to know what's the specific heat of this alloy. So then you just divide, and you're going to have the specific heat of the alloy is 500 about. So there you go. So it's not too hard to use a calorimeter to figure out specific heat. I mean, that's something that we could do in class. Maybe we'll do it as a lab. Actually, it sounds like a pretty cool lab, so I'll think about it. See what we can come up with. All right, one more question. This is called a bomb calorimeter problem. So it's a little bit different. Let me see if I can extend this page a little. There we go. But it's basically the same concept. Okay, so a bomb calorimeter is basically what you use when you want to burn a substance and see how much energy is produced in that burning process, or how many calories are produced, or whatever you have. So you burn the substance, you place that inside what's called the bomb. So basically it's the same principle. You've got a vat of water, it's surrounded by the insulating material, and you stick a thermometer in to measure stuff, but mainly what you do is you stick this little guy in there that's been heated up a lot. That guy's called the bomb. And inside that bomb is just some melted down substance. So yeah, that's pretty much what you're doing. So they say the bomb is placed in the water of the calorimeter, and a fine wire passing into the bomb is then heated briefly, which causes the mixture to ignite. So I guess you heat it up kind of once it's in there, because think about it. I mean, if you heated it up before you put it in there and then stuck it in, you're gonna miss out on that original heat loss, because it won't be measured as it's outside of the water. So you like light it on fire while it's in there. So that's got to involve some kind of special equipment, but that's basically the idea. All right, so let's say we have a problem and it says, like in 14.6, determine the energy content of 100 grams of some fudge cookies from the following measurements. So we've got a 10-gram sample of cookies. They're put in a bomb calorimeter, and then it's submerged, and then it's lit on fire. So then they're ignited. So it says the bomb is made of aluminum, and it's placed in water, and the cup the outside, I guess the outside container is also aluminum. So you've also got to measure the heat that goes to the outside of the container. So yeah, I guess I should have been, instead of just calling this an insulator, like this thing is actually, there's like a cup out here that also is going to take some of the heat. So yeah, all right. So all we're going to do here is basically, that's the info they gave us. They gave us the mass of the water. They gave us the mass of the aluminum bomb, which has the cookies in them, so you're not really going to worry about that 10 grams until the end. They said after this happens, it reaches 36 degrees, the total temperature of everything, and its initial temperature was 15 for everything, and they gave us the mass of the cup. So basically, we're just going to say the sum of Q. So if you look in the book, Q is like the heat released, Q is like the symbol for heat, I guess. So the sum of all the heats involved are going to be the ones from water. You've got the ones from the cup. So a little bit of that heat's going to like hit the edges of the container. That's where that comes in. And then you've got, of course, the heat from the bomb container itself that the cookies are inside of. So you've just got all those different things, and so you can just factor out that change in temperature at the end. As we said, they're all going to undergo the same thing. We're just looking at the entire system. So all you've got to do is plug in the numbers. So we said that the water was 2 kilograms. So we're going to go 2 water. We had specific heat was just, well, it was, let's go back and look. So water was 4186. In this one, let's see what they asked us. So it said determine the energy content. So I think instead of using this unit this time, this is one of those times where we might want to go for like calories. So I mean, don't worry about it too much, but let's just go for calories this time. So instead of using 4186, that's what we're going to use, that value of 1 for water. So there you go. So we're going to use 1, and the units are going to be kilocalorie per kilogram. So let's just put those units in this time, I guess, to make it a little easier on ourselves. So we're going to have 2 times, let's see, so that's 2 kilograms. Better write that down. And then we've got C, it's going to be 1 kilocalorie per kilogram degrees Celsius. And then we've got the same kind of thing for the other ones. So the mass of the cup is 0.524. So you can see that these already cancel out and stuff. So you get kilocalories times degrees Celsius. So we'll worry about that in a sec. Plus 0.524. I'm not going to keep writing it. So that's kilograms. And we're going to go grab the value for, we said aluminum, so we're not going to use this one. We're going to use this one this time. So we're going to go times 0.22, that was, right? So that's 0.22 kilocalories per kilogram times degrees Celsius. So I'm not going to keep writing that down, just too much stuff. Plus, we said the bomb was also aluminum, but it weighed a little different with those cookies inside, so it was 0.615. And we're going to use that same value for a specific heat. Okay, so all that stuff times the change in temperature for the system, which is just going to be 36 minus 15. So if we do that out, and I guess these are degrees Celsius, what we get is, let's put all these guys had their degrees Celsius on the bottom. So like when you do all of these guys, like this degrees Celsius is going to cancel this out and you get calories left. So that's going to achieve what they asked us with our energy. So we just stick that in our calculator and we get 47. And like I said, we get kilocalories since we did it this way. So that's how much 10 grams gives us. But we've got to be careful. So they said do it for 100 grams. So if we do it for 100 grams, then we're going to have to multiply by 10. So instead of 47 kilocalories, or remember a kilocalorie is the same thing as a calorie, the thing that they put on those energy descriptions on food. So that's 47 calories for 10 grams, so 100 grams of this fudge cookie, decent amount, is going to give us 470 calories that we're going to have to burn off later. Oh my gosh. Remember also that idea about like the body's only like 20% efficient, so don't despair. And they really did say determine the energy content. So remember, if you want the energy content, that's really like the heat kind of value. If you want the energy kind of value, you just convert units, right? So if you want, let's say 40, let me get a different color down here. So if you want the energy content, you would want to go like, let's see, so we'd go 470 kilocalories or calories, so we'll go kilocalories because I think the book has a nice conversion for that to joules, right? So kilocalories to joules, how does that work? Let's see, back on page 385, it says 1 kilocalorie is 4.8, no, 186 joules. Then we get those to cancel, and that's how much energy that little heat transfer accomplished. That's going to be 1970 if you do your calculator, and you do significant figures, right? So that's 1970, I think it's times 10 to the third joules, so kilojoules. Let's see, I'm going to check that in my calculator, I don't trust the book. 470 times 4.186. Oh. Yeah, I really shouldn't trust them. This isn't joules, that's conversion for kilojoules. So, no 10 to the third. Ah, so if that's the conversion for kilojoules, I guess actually it is 10 to the third. Trying to confuse you, sorry. Anyway, so hope you found this video useful.